Hello, everybody. Welcome back to this new episode of this series. We are trying to write our kernel from scratch. Last time we started working on our physical memory allocator. So that's what we are going to continue doing today. Let's get to it. Right. So this is where we left it off last time. We've created a base for our work, and we just had the implementation left to be done. So I guess let's get started on that. So here in init ranges, what I will do is actually take the ranges that are defined in map entries here and put them into this list here, or actually these three lists here. So memory ranges, free ranges, and reserved ranges. So let's get to that. So I guess we are going to go for all mmap entries, and for each entry, I guess we are going to check. Well, before we check, I guess we can just go ahead and create or add this entry here to memory ranges. So to do that, I am going to create a const range, which should be of type mmap. It's physmem. Range, yeah, sure. And this here would be, so it would have a start, should be entry.get pointer, and a length, which would be entry.get size, and I probably will add a type, which should be entry.get type. Sure. So okay, we don't have a type, so let's go here and we'll add a type. This would be memrange type, I guess. Sounds good enough. So const memrange type, and this would be an enum. Yeah, sure, this would be an enum, and then we'll have to basically have the same entries that we have on the other enum from our boot info. So I'll just go here, copy those over here, and yeah, I'll just do this because we are currently on Zig 0.15, and all enum items are now lowercase. Right, so now that we have this, actually we are going to also need a function to basically convert between the two types. So let's create a function. I'll call this actually, never mind, I can just go ahead and put that function in here. So this can be a public function from a map type. Sure. A map entry type. I think it's cool. So this one here will take a type, which is it's called type with an E. And this here would be boot info.mmap entry.type. Yes, of course. And this would return a self. Maybe something like this. And here we are just going to return enum from int. So int from enum of type. Sure. I'll just mark a to do make this a bit more resilient in case we change something or we add some other stuff to our enum there. Right, so now we have our range. Let's put our range into our, so we have a list that has a type of FISMEM range list item, and the range goes into there. So we need to create those items, and for those items we are going to need an allocator, I think. Right, so let's do something like allocator.create, and the type is fis mem range list item. That's pretty much it. So let's create mmlock. That should be somewhere here. This one, just do this. This in it here, we take an allocator here. Of course, we need to define it. So const allocator is mem allocator, I think. Yes, and since this init here is called here, so this needs alloc, and this needs to take alloc. Yes, looks pretty good. That looks pretty good. So I guess this one here needs to be var, and I guess we could do something like this and just initialize it with sure. It's never mutated. Ah, okay, yes, sure. It's the content that's mutated. Right. So now we can actually just go ahead and do memory ranges.append list item. Sure. What we are going to also do is, so depending on the type, if it's free or not, we are going to also create an item for either the free ranges or the reserved ranges. So actually, let's extract, let's go with pointer entry dot get pointer. Let's extract all the data from entry. Size is size, and type is entry dot get type. Right. So if we do this and go pointer, and do size, we've called it, and do type like this. Right. So here, if type is free, right? So here we are going to create a new list or free list item. So this would be alloc.create, same type, FISMEM range list item. And we also need to create const range. No, the range would be the same, I think. So free list item, deref that, and set a new value for range to be range. Yeah. Actually, never mind. Don't do that. Okay. And here we'll need an else. Oh, of course, free ranges. Then free. Come on, less item. And of course, let's not forget about free pages count. This would need to receive so a div exact, if I can spell that, of size by constants arc page size. And I think we don't have constants yet in our kernel. Yes, we don't. So let's create constants.zig. and do public const arc page size is 1 left shifted by 12. Right, and now we just need to, I guess, import that. So constants is import constants.say. There we go. Right, so here for our else, we are just going to go the lazy route and do free becomes reserved. And that's all it takes. Right, so now that we have initialized all ranges, I want to go ahead and print the ranges. Right, so I want to print the ranges. So let's go for memory ranges as range. Not need to change it. We can do something not debug, and we can actually just go any. And we can go range, sure. And we might also just go ahead to this range here and do something like this. Actually, let me fix this. We don't need options, we don't need a format, we just need the writer, and we can try to print so list item, and we can do something like this. So it has a range, should be any. Then it has a previous pointer, which would be just a hex value. Sure, something like this. Let's actually do something like that. So here we'd like a so let me think about this. We'd want the address of self. Yeah. Then we'd want self.range. Then we want self.prev and self.next. Right, that looks pretty good. And now if I go up here, let's create format for this. Again, we don't need the format or this there. We can try writer.print, and here we can go range. Go for the same things again. Should probably do something like this to something like this. Size is in just bytes, or actually let me just have the size in hex. And we can just write the type as a string. Yeah, sounds pretty good. And here we need self.start, self.start plus self.length, then self.length, then tag name of self.type. Yeah, that sounds pretty good. So let's build this and see what we have. Okay, so I guess we need to pass in the allocator. And I think the allocator comes in from here. This would need to be, actually, before we do that, I'll get rid of this. Before we do that, since we are going to allocate, I think this function here would need to be, so this needs a try, since it will probably return an error. All the alloc.create would need a try also, I think. Yeah, sure. That looks okay for now, and means that now if we go to main, this here needs to try, so it go into failable main. So pmm.init, and we'll pass it heap.permanent allocator. Sure, why not? So let's let me just check that we have master. Yep, okay, cool. So now if we build this back up, no field named alloc instruct. Oh, right. So I have, yeah, I initialized it, but I didn't create it. So allocator. Let's go. Expected type pmem range type, but got okay. That's fine. So where was that? It was here. So this would be from. This would need to be mem range type from. Okay. Missing struct field priv. Oh, right. So this needs to be initialized to null. And error is not indexable because it's not a range. Right. Okay, so this complicates the thing a bit. We can't do this. What we are going to need to do instead is, so let's do iter is memory ranges dot iter. Sure, it doesn't exist. We'll create it. And here we should do iter dot next, and this one here would become a while. Okay, sure. And now we need to go to list. So somewhere here, public function iter takes self as just self and returns a iterator. Yeah, of t and next field, and return. Let's say that we just have a current field that we initialize to self.head. Yeah. Okay, so let's create so public function iterator, which takes a comp time t time any type, and then a next field, which is a stud meta field enum of t. And of course, we return a type, and this type would be a struct. Let's do this, and here we are just going to go the lazy route, create this. Then we'd have a public function next, which would take a self as a pointer since we are going to mutate it, and this would return an optional pointer to t. Yeah. Yep. Right, and here we'll have the current, which would also be an optional pointer to t. And here we'll have const. So let's think about this. Const current value should be self.current if current value and is not null, basically, we can do self.current is at field of current value. Next. Duplicate. Oh yeah, okay. So this is one of the new additions to Zig 14 and 15 and master, basically. You cannot have a field that has the same name as a function. So let's call this next next item. Sure. Next item. And of course, we need to const self is this here. And of course, here we return current value. Right. Looks pretty okay. Probably write a test for this to do test for this. That should be fairly easy. And actually, since we are already writing iterators, let's call this forward iterator and make a backward one. Oops. There we go. So this one here would be backward iterator, and this would take a prev field and we will do pretty much the same thing, except that this one here I'll call prev instead, just so that we know that we are going backwards. Right, and let's also plug in the, let's call it reverse iterator. Takes a self, and it's basically the same implementation of the and prev field. So if I can forgo the fact that this is called prev, I could probably reuse the same struct here for both forwards and backwards iterators. Sure. Let's go ahead with that, I think. So this one here would just become iterator, and this I'll call field. Yeah, sure. So this one here would also be iterator, except that this would return a current which is set with self.tail. Yep, looks pretty good. Right, so now let's go back here. This should just build. Let's see. So here we have a format problem. Format problems are the worst. So we have an any here. Where else do we have a format problem? One of these. So we have 1, 2, 3, 4. 1, 2, 3, and 4. Yeah, I'm not sure. I am not sure where the issue is. Optional. Cannot format optional without a specifier. Oh. Huh, right, okay. Cannot format optional without a specifier. So is this? Well, no, we actually do have, oops, we do have a specifier there, so what are you on about? Yeah, I'm not sure what this is. Oh, right, okay, I see it. It's my bad. We are probably talking about, so int from pointer. Yeah, sure. Int from pointer. It's so bad. The error message is so confusing. Right, let's build this. Or rather, let's run this and see. Oops. What's going on here? Hold on a second. So self. Okay. Right. So let's take a look at this. So we have this first item here. Well, okay. So first of all, this is not what I wanted to do. Or rather, it might be what I wanted to do. But what's weird is all of them have the same address. Which is kind of weird. Why do all of them have the same address? Oh, hold on a second. Self here is passed as a value, so it can actually have been copied. So, right. Let's try something like this. Sure. Let's just go with self here. Let's see if this builds. Okay, right. Let's see, do we have... Okay, so now we do have addresses. Cool. So let's first stop this, go up here, do this. Yeah, probably do something like this also. And let's not forget to take that by address. Right, so, oops, go. Let's build that. Let's run that. Okay, and now we should just see nothing. We still have the same issue on the ranges for some reason. Why is that? So range is any it's getting passed by value still. Okay, let's see if this helps. Okay, it does help. Cool, very cool. Right. So we have the next pointer of this range here is 4140D0, which is this one here. So that's pretty cool. this one goes to this one. So at least we know that our list is actually working. And we do have our entries. I might need to do some math here to check that we have all the memory we've mapped. But I can already see that we have an issue here because this size here is way too big. This is yeah, this is way too big and it's used. I don't think we're using that much memory. This size here looks like it's our free size. But yeah, I think this entry here should not exist. I also see that we have contiguous free blocks. I think one of which was reclaimable, and we've reclaimed it, but we did not merge them. So we might want to try that. And here we also have contiguous free blocks, but this one here ends at this address, and this one starts quite a bit further up. So they can't be joined. Whereas these two, so this one ends here, and the other one starts right after it. So they can be joined. Right, let's work on that. Okay, so I guess that's something we are going to do in reclaim freeable memory. So the way we are going to do this is just get a variable. Let's call this index. Set that to 0. And create a second variable. Let's create the second variable. Let's call it last index. Set to null. Might want to give them types. So this would be U64. Right, and we are going to get rid of this here. So while index is less than a map count, I think. No, we don't have that. So a map entries dot length. Sure. We capture nothing. And we might, yeah, let's just use this here to do index plus equals 1. And let's create const entry is map entries at index. Sure. So we are going to get rid of this continue block here, replace that with something like this. Yeah, so this one here needs to become this. So if we have a reclaimable block, we mark it as free. And in either case, if last index as li, and if, so let's call it last entry is map entries at li. So if last entry dot get and is equal to entry dot get pointer, and they have the same type, dot get type is entry dot get type, then we can consider merging them. So last entry dot size plus equals entry dot size, and we set entry dot size to 0 for now. Oh yeah, of course, this language uses this version of and. Right, so now we need to initialize last index. So we are going to go all the way down here. So keep last is equals to true. And if keep last, well, if not keep last, then we set last index to index. And we are going to create const keep last, should not be const, should be a variable. This would be to false by default. Yeah. So if we change anything with the last entry, then we should keep the last entry, increment the index so that the next one, if it's free, would need to be merged with the same last entry so that we can do one single pass. I'm not sure if all the cases are covered, but sure, why not? And here in init ranges, we might want to do if size is 0. Let's skip that. Okay, so let's see here what we messed up. Cannot dereference a map entry. What? Sure. Sure, okay. Cannot assign to constants, that's fine. Oh, right. So I'll just keep that output there so that we can compare. And I will just rerun a new one. Let me just check 6 gigs. Okay. All right, so let's check this one. Okay, we do still have the problem, so that's not been solved. Okay, so let's go back to here. So what's going on? Okay, so for the first iteration, this would not be executed. Right, so let's add, so log.debug comparing so this one would be last entry and this one would be entry. Okay, so at least it does go through all of them, but it does not increment the last entry, though. So this one here, oh, okay, right. My bad, I guess. Right, let's see. Okay. And here we can see that the two ranges here got merged. Let's just make sure of that. So BD, CD, and BD, CD, C. That one was 124, and the other one was 1D, so it should be, let's compute that, plus 0x 1D, 3 zeros, never mind. So let's do this. Let's go to plus 1D, 141. Huh. And what did we have here? Yeah, kinda weird. Kinda weird. Okay, so let's see here. We should at some point see the same address twice. Yes. And here we compare it with, so it had this size here. And here it has this size here. Okay. I think I might know where the issue is. Yeah, maybe not change that. Okay. Let's see here. Okay. 144, is that what we expected? 141. Where did the additional stuff come from? So we should see a repeat, should be around here. So this one had this value. Yeah, I'm unsure about this. Okay, so let's add a few more log entries then. Okay. Yeah, actually, let me just do something before we go any further. I'm just going to go over here and do format just to simplify this. So again, this does not exist. Does not exist. We're going to need to import stud. Oops. Go on. And this need to be try print. And we'll do the same thing again, where we go. So it goes from this to this with a size of keep in hex and a type of string. Sure. So this would be self. And of course, let's not forget to take this as an address. So this would be self.start, self.get pointer. Actually, simplify this. Self.get and self.get type. Tag name of that. Right, let's try this again. Too few arguments. Right. self.get size. Oops. All right. Okay. A bit more verbose than earlier. So let's see where we are comparing. So this one would be 3, and this one would be 3, right? So this one has a size of 1 to 8, 3 zeros, and this one has size of 1 D, 3 zeros. Okay, so it looks like this region here has grown. So if we take the same region again, we have the size here that's been basically the sum of these two sizes. That looks pretty okay. And here we should be comparing this one, which is fine. So we do actually have an okay working algorithm here. Right, so that's pretty cool. Let's let me get rid of this. Just keep the other one. Cool. So now we can go ahead, go back here, maybe remove all the clutter that we've added, and let's try to move on. Oh, we actually still have one more issue, which is if we go ahead and let's track total memory just for now. So this would be plus equals. Yeah, sure. Something like this. So mind you, this is physical memory, so we should, in theory, have the memory, the exact same value that we've supplied when we created our VM. So memory is of type U64, and that should be okay. So if we track the total memory and we just print it out here, total system memory is, let's print in hex and do total memory. Right. Because I think we do have a problem there, but just to be sure. Okay, so go to the trusty calculator and look here, we have 19 gigs of memory, which is quite a bit since we've supplied the VM with just 6 gigs. So we do have a problem somewhere. And actually, if I go back and just subtract this size here, so let's go back here, just do this, we can see that we find our 6 gigs of memory. So this last entry here that we've added to our list is coming from somewhere, and it's totally wrong. So let's see what the issue is. Because here, what we are doing is we are taking the boot info memory map. We take the size of the header. This one should be fine since we've actually logged how long it should be and what we got, so that's fine. Memory map size is 432, and we have 16 bytes per memory map entry, so we should have 27 of those. And here we are getting told that we have actually created 27 of those from our bootloader, so that should be fine. So if we count these, should have well, now we've merged them, so we can't know, but yeah, so we do have 27 of those. If we count this one twice, since this one has two segments merged. So that means that we have a problem on our bootloader side. So let's take a look at our bootloader then. So get a map. Oh, memmap, okay. Right, so here we take the mmap size that we get from here. We add a few or just a couple descriptor sizes to it, and we allocate that size just to be sure that we have enough memory. Since calling allocate pool would actually try to allocate memory, so it could create a new mmap entry. And then here we call get memory map again. So memory map, if we go to the spec, we expect memory map size, which is the first argument we pass it, to have the size. So on output, it is the size of the buffer returned by the firmware. Yeah, so we expect that to be the size of the actual memory map. And we go ahead and basically loop over those, or we compute the number of descriptors, and then we loop over those and add them to our mmap entries, which is a view onto bootinfo.mmap. Right. So first thing I want to add here is I'll just do div exact. So we divide mmap size by descriptor size. Descriptor size. I believe that's what we had, yeah. Right, so this would panic if this division here is not exact, but it should be in any case. And then we go on to pick our descriptor from index size and the address of the memory map. Where does this address come from? Okay, so this is the mmap that we get returned by the call to memory map. Right. Okay. And then we just go on and create our entry. Physical start, number of pages, entry type. And we pretty much do the same thing here that we just did on the other side, on our kernel side. But I think we did something a bit more complicated here. It could have been simpler, but okay, fine. So here we create a new entry from that entry, and that should be okay. Huh. Right, so does the documentation say anything about okay, so we should be fine, I think. All right, fine. Fine. Let's go to our main, and I'll just dump a few mmap entries. So let's put this as info, and let's just do I think we can replace Let's leave it be, I think. Let's just leave it be. Let's rebuild this. Okay. Right. So we do have this entry here. It's kind of weird. Let's, I guess, add a few map. Let's print the memory map descriptors that we get. So for entry, we should probably put back this here, info. Right. So all of these are okay. And then here we have reserved memory type. Huh. So I guess we do get that page in our... But what's weird is its attributes are 0. So what are 0 attributes? Actually, there are no 0 attributes. So why do we get that then? If attributes cannot be 0, then we surely are mistaken somewhere. Let's do this. Sure. And from... no, never mind. I'll just do this. Okay, so hold on. Okay. So I guess I just need to know where the style is and the size of our descriptors. So where do we have those? I guess we could do... No, not this one. Maybe somewhere here. Yeah. Log.info. Map size is that, and descriptor size we already know. That's descriptor size. Let's just put it back here, and here let's just do something like that. So we'd have a map. Yep. And then we'd have a map size. Then we'd have descriptor size. Right. Okay, So let's see what we got. So 1018, that's correct. The size is 118, so we expect to go to F818. And the descriptor size is 30. Yeah, so that should be fine. Okay. So let's go ahead and check. 30 is 48, decimal, that's fine. And 800 is 6144. So for some reason we are getting well, okay, fine then. I think I'll make this easy on myself. Cool. So now I'm just going to once we get the descriptor, I'm going to check if descriptor dot attribute. I'm going to bitcast that to AU64 and just continue if that's the case. Rather, if this is equal to 0. So I just don't want the 0 attribute descriptor entries in my memory map. So let's see if that fixes my problem, but I hope it does. Right, so now we actually have the correct memory size. Cool, very nice.